In 2019, two distinct environmental catastrophes occurred simultaneously. Severe floods displaced hundreds of thousands, while intense bushfires consumed millions of acres. This map shows the climate engine behind these events, the Indian Ocean Dipole. It is defined by the difference in sea surface temperatures between the western and eastern parts of the ocean. During a positive phase, the western pole experiences a significant temperature increase. This chart shows the result: heavy blue bands representing rainfall up to 300% above average across East Africa. Simultaneously, the eastern pole cools. This forecast for Australia shows dark red zones where extreme maximum temperatures and drought conditions became highly probable. This graph tracks the dipole index over time. The sharp peak in late 2019 represents one of the strongest positive dipole events on record, far exceeding standard seasonal variations. The Indian Ocean Dipole functions as a coupled global engine. Because these sea surface temperature shifts regulate weather patterns thousands of miles away, climate models must capture these dynamics with high fidelity to accurately assess global climate risk. Analytically, there is a specific challenge in modeling this system. The dipole does not oscillate symmetrically between its positive and negative phases. This comparison reveals a persistent physical skewness. In Panel A, the positive phase, a massive zone of cooling dominates the eastern Indian Ocean. In Panel B, the negative phase, the warming in the same region is much smaller and weaker. Traditional climate models have historically struggled to replicate this skewness, leading to significant gaps in forecast accuracy for the most extreme events. Resolving these model biases requires looking beyond surface-level data. The evidence suggests the primary driver of this extreme asymmetry isn't horizontal wind or lateral currents, but subgrid vertical mixing. If climate models fail to account for this vertical cooling mechanism, their ability to project the frequency and severity of future climate events is limited. To isolate the cause of this cooling, researchers use a mixed-layer heat budget. This mathematical framework tracks every unit of thermal energy moving through the surface layer of the ocean. Previous studies suggested that nonlinear horizontal advection, the lateral movement of water, was the main cause of the dipole's asymmetry. These studies often relied on offline heat budget calculations, which use monthly average data that can obscure high-frequency physical processes. This chart shows the results of that offline approach. The large violet bar represents a residual, effectively a significant amount of heat energy that the model cannot account for. In Chart A, researchers used a regional ocean modeling system for an online calculation. By calculating the budget at every time step, the residual bar is eliminated, closing the mathematical loop. With the mathematical errors resolved, the high-frequency data identifies a specific driver, the orange bar, representing vertical mixing. During a positive dipole event, this downward orange bar shows that vertical mixing becomes the dominant force, pulling cold water up and cooling the surface. During a negative event, this effect is much weaker. Vertical mixing is reduced, which prevents the surface from warming as intensely as it cools during the opposite phase. By closing the heat budget, researchers demonstrated that vertical dynamics, processes occurring beneath the waves, directly dictate the temperature extremes we observe at the surface. To understand how this works physically, we need to look at the water column in the eastern Indian Ocean. During a positive dipole, intensified southeasterly trade winds push surface waters away from the Indonesian coast toward the west. This displacement causes coastal upwelling. The thermocline, the boundary between warm surface water and cold deep water, is pulled upward, closer to the surface. As the thermocline shoals, the temperature just below the surface layer drops significantly, as shown by the steep curve in this temperature gradient data. This creates density stratification. The cold water below is much denser than the warm water above, creating a stable boundary that naturally resists mixing. At this stage, the trade winds have created an extreme thermal gradient, with a massive volume of cold water sitting just below the surface layer. Breaking this density barrier requires a specific kinetic force, vertical shear. Vertical shear occurs when there is a sharp difference in current velocity between the surface and the water below, generating turbulence. Those same intensified trade winds accelerate the surface currents, creating the high levels of vertical shear necessary to disturb the water column. The kinetic energy from this shear overcomes the density stratification, physically shattering the boundary between the layers. This process is captured in the vertical diffusion coefficient data, which spikes as the mixing intensity increases. This churning pulls the cold subsurface water into the surface layer, resulting in the extreme sea surface cooling characteristic of a positive dipole. In the negative dipole, the winds relax, meaning there is less shear to break the stratification. The cold water remains at depth, dampening the potential warming at the surface. The thermal asymmetry of the Indian Ocean dipole is a direct result of the interaction between density stratification and kinetic wind shear. One question remains: is the ocean's behavior simply a passive reaction to the strength of the winds above? Researchers tested this by using the Equi-Nu index to normalize the heat budget against the actual wind force. This chart shows the heat budget data after it has been adjusted to mathematically equalize the wind force between positive and negative phases. Even when the wind strength is normalized, the vertical mixing term, shown here in orange, remains disproportionately larger during the positive phase. This proves the ocean's thermal response is inherently nonlinear. Its internal mechanics amplify temperature extremes independently of atmospheric forcing. These subgrid oceanic processes have significant implications for our understanding of global climate change. Increased greenhouse gas emissions are altering baseline ocean temperatures and thermocline depths worldwide. If current emission trends continue, models project that the frequency of extreme positive dipole events will increase from once every 17 years to once every 6 years. This means the cycle of severe bushfires, droughts, and flooding events seen in 2019 could become a much more frequent occurrence. Accurate climate risk assessment requires models that account for these vertical mechanics. Understanding this subsurface turbulence is necessary to project the future frequency and intensity of these global weather extremes.